Hi, and welcome to Properties and Structures of Matter. And today we're looking at inquiry question 4, all to do with bonding. So our question today is, what binds atoms together in our elements and in our compounds? So the syllabus outcomes we're going to be looking at over the next couple of videos is looking at the role of electronegativity in determining the covalent and ionic nature, the differences between those compounds, looking at different ways of naming their valency and different ways of writing their chemical formula, including Lewis dot diagrams, looking at the spectrum of bonds and modelling some of these shapes. So let's get started. So we've just touched on recently electronegativity when we were looking at the trends of the periodic table. And so just to recap, the electronegativity is the power of an atom to attract electrons in a covalent bond. And so we will have noticed that as we move across the period, we are going from a weak electronegativity to a strong electronegativity. So it's that affinity to attract those electrons there. So how does this have to do with our bonding? So our electronegativity is the measure of an ability to attract that electron. And that's a real key determinant in determining the nature of the bond that is occurring there. So when we look at ionic bonding, it's a force of attraction that happens between our anions and our cations. And with our covalent bonds, it's the force of attraction between two nonmetals. So let's look into this a little bit further. So if we look here, we can see here we've got a number of different types of bonds. And we're going to look into this a little bit more in detail. So there are our non-polar covalent bond. That is when the electrons are shared equally between our two nonmetals. And a good example of that is chlorine. So if we have a look at chlorine, if we look at chlorine's electronegativity, they will even each other out there. So it will end up having an overall affinity of, say, 0. So chlorine-chlorine bond is a covalent bond. It's between two nonmetals, but it's a non-polar one where those electrons are shared evenly around that chlorine atom. However, the polar covalent bond is something a little bit different, and the example that we have here is our hydrochloric acid. And if we actually look at the electronegativity of hydrogen compared to chlorine, the difference between those two is not great, but it's certainly not 0, and it forms what's called a polar covalent bond. The other type of bond that we have is our ionic bond, and our ionic bonds are where one electron, they're not shared, but one atom actually takes that electron from the other atom, and there is a large difference and a maximum difference between their electronegativity values, and we'll have a look at some of those examples in a minute. So this is a continuum. We can have a continuum from down this end where we have our non-polar, and we usually have a difference of about 0, all the way up here to our maximum, and this is a strong ionic bond. Now when we have a strong ionic bond here, there is something between here. When does it become a non-polar covalent bond, and when does it change to a strong ionic bond? And it's a continuum there. It's a little bit of a blurred region between when it becomes from one to another, but the general rule of thumb is around about between 1.5 and 1.7 in the scale, in the electronegativity scale, is around about when we would say that change occurs. So having a look here, and this there's a spot for you to record some answers here into your work booklets. To form an ionic bond, one atom has a stronger attraction for the electrons than the other one. So when we have that subtraction, it might be 2.3 is the difference between the two the cation and the anion, and it has a real strong attraction. The chlorine, for example, in sodium chloride has a real strong attraction for those electrons, and therefore it forms our ionic bond. To form a covalent bond, they tend to have a similar attraction. There's not a large difference between their electronegativity values, so they're more likely to share the electrons than to actually give them away. So the general rule of thumb, as I've just discussed on the sliding scale before, if the difference in the electronegativities is greater than about 1.5, they'll form ionic bonds, and if it's less than that, it tends to be covalent. The difference then is it a polar covalent or a non-polar covalent? So let's have a look at a couple of examples. For example, hydrogen's electronegativity value is 2.20 and sulfur is 2.58. So if I'm making hydrogen sulfide, the difference between them is only 0.38. It's not very much at all. So it is much less than that 1.5, and therefore we have a covalent bond there. And it's these differences in our electronegativities that help us determine whether it's going to lose or gain an electron there. So looking at this table, we have got sodium chloride. Chlorine has an electronegativity of 3.16. Sodium has an electronegativity of 0.93. So is it going to be ionic? Is it going to be polar covalent or non-polar covalent? So again, looking at that sliding scale that we're talking about, where 0 is our non-polar, all the way up to around about 4 will be our ionic, and then in between at around that 1.5-ish mark is our polar covalent. So in the case of sodium chloride, we are looking there at an ionic bond. That's not written very well there. So we've got our ionic. So looking at magnesium chloride, it has a difference in its electronegativity of 1.85. So again, greater than about that 1.5 to 1.7. Again, it's ionic. So now we look at aluminium chloride. Now it's 1.55. It's still a transfer of electrons, but it's not as strongly the strong attraction that we have with the others. So it is still ionic, but it's again a little bit closer to that grade area. So looking here at silicon chloride, we are looking here at our polar covalent. Potassium chloride, about 0.97. So again, we're probably looking there at our, it's closer to that 1.5, probably around our polar covalent. As you can see, it's very grey. Looking at sulfur chloride, we're down around that 0.5, so we're looking more at non-polar covalent. And chlorine, you can see there, because the difference in electronegativities is 0, it is non-polar covalent there. We'll have a practice at some of these in class and do some questions. Talk to you then.